Welcome. Let us now look at something called a Gibbs Duhem equation. This is a fundamental equation in classical thermodynamics, and as we go along let us see the features of that, but now let us derive the Gibbs Duhem equation. Let us consider equation 215, which is dgt equals minus st dt plus vt dp plus summation of mu I dni. Now this is a differential. Let us integrate this equation at constant t and constant p. If it is constant t, this term will completely vanish, and if it is constant p, this term will completely vanish. And also let us retain the relative proportions of the components in the system while we are integrating the equation, which means the mu i's are also being held constant. Integration can be viewed as increasing the size at this under the same conditions as the small aspect that we initially looked at. Therefore, if the initial values were ni, gt, st and vt of the system, the final values when it has been integrated or it has been made big could be kni, kgt, kst and kvt. The values have increased k-fold. It is quite easy to see, these are all extensive quantities. If you have k number of moles, the other variables are going to increase k times, and therefore it is quite valid to write this, and we are viewing the integration as increasing the size of the system. Okay, now we are integrating this equation dgt minus st dt equals minus st dt plus vt dp plus summation of mu I dni, and we are looking at this integration as increasing the size of the system. Initially it had let us say 1 mole, and it is now going to k moles, and therefore the values of the extensive variables initially were, let us say, ni number of moles, gt the total Gibbs free energy, st the total entropy, and vt the total volume, to the final values which is k times that of the initial values. Now if we do that, the delta gt, which is the integrated value, the difference between the values of the two states, say 1 and 2, delta gt equals, since we had taken it at constant temperature, the first term turns to 0, at constant pressure the second term goes to 0, and the third term summation of mu I delta ni, where delta gt equals kgt minus gt. Remember I mentioned about the difference between the final value and the initial value, and therefore which can be it can be written as k minus 1 times gt, and our delta ni is nothing but k times ni minus ni, which can be written as k minus 1 times ni. Substituting these values back into the integrated expression, k minus 1 times gt equals summation of mu I into k minus 1 times ni, or this k minus 1 is a constant, it can be taken out and cancelled, gt equals summation of mu I ni. Let us call this equation 223a. From that equation, delta g equals summation of mu I ni. If we take the total differential of that expression, we get dgt equals mu I dni, the first term, the first function into the derivative of the second function, but it is summed over all terms, therefore this will just be a sum plus the other part of the differential in the chain rule Ni times d mu I. Let us call that equation 2.23b. If we compare 2.23b with 2.15, I would like you to compare yourself, we can write minus st dt plus vt dp minus summation of Ni d mu I. If you substitute the expression for dgt and cancel the common terms here, we get minus st dt plus vt dp minus summation of Ni d mu I. This mu I dni will get cancelled with plus of mu I dni, which appears in dgt, and that equals 0. Let us call that equation 223c. This equation minus st dt plus vt dp minus summation of Ni d mu I equals 0 is called the Gibbs Duhem equation. Note, although we, while deriving this equation, we had made assumption about constancy of temperature and constancy of pressure, the final equation that we have is in terms of state variables. What does a state variable mean? Its value depends only on the state of the system and not on the path taken to reach the two states. A constant temperature process or a constant pressure process are all paths between the same two states, and therefore whatever had been the path, say a constant temperature and a constant pressure and so on and so forth, this final equation here is valid for all conditions because they are in terms of the state variables. Note the variables that are here: St, the total entropy, which is a state function; temperature, state function; Vt, it is a state function; P, pressure, state function; Ni, the number of moles, depends on the state; mu I definitely depends on the state. Therefore this is a variable of this is an equation of all state variables, and therefore this is valid in general. Also note that this equation is the relationship between simultaneous variations in the intrinsic parameters. That is what makes this equation special. This is temperature, this is pressure, this is chemical potential, dt the variation in temperature, dp the variation in pressure, and d mu I the variation in chemical potential, and this equation gives us a nice relationship when all three are varied simultaneously. That is the another special thing about the Gibbs Duhem equation. See you in the next class.